Hello, sir, and my fellow batchmates. Myself, Otanu Banerjee, from third year Electronics and Communication Engineering Department at Kojmir Government Engineering College. Here is my CA1 presentation. Today, my topic is pulse code modulation, and the subject digital communication and stochastic. Let's start the topic. Pulse code modulation. Here is the introduction. Pulse code modulation is the name given to the class of baseband signals obtained from the quantized pulse amplitude modulation signals by encoding each quantized sample into a digital word. For baseband transmission, the code word bits are transferred mid to pulse waveforms. Here is the definition of pulse code modulation. Pulse code modulation is known as digital pulse code modulation technique. In fact, pulse code modulation is quite complex compared to the analog pulse code modulation techniques, in the sense that the message signal is subjected to the great number of operations. When pulse modulation is applied to a binary symbol, the resulting binary waveform is called a pulse code modulation waveform. Let's talk about key idea. The concept of converting continuous timing varying signal into a digital sequence. First of all, easily stored in memory device, and other one processed using computers or digital signal processors, and transmitted over like distance without significant degeneration from noise. Now, see the advantages of pulse code modulation. It's high noise immunity and easy to process, and it's very secure and compatible with digital switching and networking. Here is the block diagram of pulse code modulation, and here is the pulse code modulation. First of all, analog message signal goes to low pass filter or anti-aliasing filter, and then sampling to quantizer and to go binary encoder, and after that parallel to the scroll converter goes to channel and to serial to analog converter, and there are also decoder and reconstruction filter and reconstructed signal. There are three fundamental steps in pulse code modulation. They are mainly sampling, quantization and encoding. Need for pulse code modulation fundamental steps. There are infinite number of amplitudes in continuous amplitude and continuous time signal. There is no much time interval where the amplitude of signal is defined, since time is continuously. It is due to these reasons we have to convert continuous time amplitude into discrete amplitude, discrete time. Here is the block diagram of amplitude sampling. Output is only available in integer multiple of t. Since t is constant, so the time axis of discrete time has variable n.
More is the quantization level, more is the accuracy of the signal. It's quite obvious. Quantizer can be broadly classified into two categories. One of them uniform quantizer and another one is non-uniform quantizer. Here is quantizer division, like one of them is uniform quantizer and another one non-uniform quantizer.
Here is quantizer division. First of all, uniform quantizer and other one is non-uniform quantizer. Uniform quantizer can be divided into two categories. One is mid-rise and other one is mid-trade. Here we can see clearly mid-trade and mid-rise characteristics of quantizer. And after that, encoder. Encoder is a block that converts the quantized values into a binary code for digital transmission or storage. Each quantized level is assigned a unique binary number which represents the amplitude level. Sampler, another quantizer, and to encoder. Now we can discuss about levels of quantizer. If a quantizer has a 4 levels, encoder needs 2 bits for each level. And if a quantizer has 10 levels, encoder needs 4 bits of each level. Here, in giving the example, we can say number of bits needed equals to log L to the base 2. L equals to levels of quantizer. Next point is quantization noise. Quantization noise. Difference between actual sampled value and the quantized value is called quantization. Here is the formula of quantization noise. And quantization step size. Maximal signal amplitude plus xm and minimum signal amplitude is equal to minus xm. Step of size delta is equal to 2xm by 4. Here 2xm is peak to peak amplitude is number, 4 is number of levels. Therefore the maximum quantization error is equal to delta by 2 unit is to volts. And let's talk about uniform distribution of quantization error. For uniform quantization error is uniformly distributed in range minus del by 2 to del by 2. And here is the graph and function which is shown here in mathematical expressions. Noise power v square noise is equal to del square by 12. So we can say signal to quantization noise power ratio is signal power by del square 12 into quantization noise power is equal to P by del square by 12. So we can say step size del is equal to 2xm and 4. So SQNR is 3pq square by x square m. And now we can see signal to quantization noise power ratio in terms of bits. For q is equal to the square, and after the SQNR is equal to 3 into p into 2 to the power 2v by x square m. For normalized condition where xm is equal to 1 and power greater than 1, so signal to quantization noise power ratio is equal to 3.2 into 2 to the power 2v. And at last SQNR in dB, with SQNR dB is equal to 10 log 10 3.2 to the power v, which simplifies to SQNR dB simplifies to 4.8 plus 6v. So this is all points of pulse code modulation. Thank you, sir, and thank you everyone.